Now we are in the world of imagination. By ignoring what is inessential, we can more clearly isolate what is dramatically different in this new view of space and time produced by special relativity. This program is about time. The physical concept of time is given meaning through the way in which time is measured. To do that, we use a device that beats or ticks in a regular way, a clock. In reality, any device such as this watch has the imperfections common to all physical objects. But in our world of imagination, we can build a perfect clock. It uses light itself. Just as a mechanical clock beats time, so does a pulse of light, reflecting back and forth. In this thought experiment, we can make the reflecting surfaces quite perfect. If we call the period of the clock T, the time for each journey between the plates is just 1/2 T. This clock, being perfect, goes on ticking and never runs down. Now let's start the clock again. Only this time we're going to set the clock in motion to the left at a constant speed, which is equivalent to us going to the right at the same speed. The light pulse again moves straight up from its source, but everything is now traveling steadily to the left. However, let's look at that again and follow the movement of the light pulse. The pulse now goes further in one beat than it did before. Since the speed of light, c, is invariable, absolute, the time that it takes for one beat is also longer compared to the stationary clock. The moving clock beats with a longer period. Let's call it T prime. So special relativity implies that a moving clock runs more slowly. To find out how much it is slowed, we isolate a triangle. It contains the information about the periods both of the stationary and of the moving clock. The vertical side, the distance between the plates, is how far light travels in half a beat of the stationary clock, and that equals the product of c with 1/2 of t. The diagonal side is the distance that the light pulse of the moving clock travels in half of its beat, 1/2 ct prime. And the base of the triangle is the distance the bottom plate is displaced sideways during 1/2 beat of the moving clock. This is v multiplied by 1/2 of t prime. As this is a right-angled triangle, we have now only to use Pythagoras' theorem to give us the relation between t and t prime. In other words, the square of 1/2 ct prime is just the sum of the squares of the other two sides. We have then the general expression for the time dilation of a clock moving at a constant speed v relative to an observer. This expression can then be simplified to show that all that's important is the ratio of v and c. What we've been discussing is not a property of any particular device, but of time itself. All physical processes appear slowed down to a relatively moving observer. Now, to verify this in practice, we need to go beyond the speeds that are familiar all around us. We must go to the world of high-energy particles, where speeds approaching the speed of light are available. But to make any measurements, we need a clock that works in this environment of atomic particles.
This is a radioactive substance, and we can tell its radioactivity from the clicking sound that you can hear from the Geiger counter I'm holding above it. What's happening is that in the source there, you've got atomic particles which are exploding, they're throwing out debris in all directions, and some of it is going up through the base of the Geiger counter and being detected. Right, well, let's try the next source next to it. As you can hear, the number of clicks per second has gone down. Activity is not as great. Let's try the last source. Although it's even less. Okay, so what's going on? What's the difference between these three sources? Well, actually, they all started off the same. The only difference is that they were prepared at different times. This first one is a freshly prepared source, so it's still very, very active. This one was prepared a long time ago, and the activity is almost finished, and this is an intermediate one. If we were to take one of these radioactive sources and were to plot the activity with time, then the sort of curve we would get would be like this. It starts off at a very high value, and gradually drops away, and this is what we call an exponential curve. It's characterized by the fact that if you start off with a certain number, then you will have half that number left after a particular time called the half-life. And that is a time which characterizes the whole of the curve, so that it takes the same amount of time to get to a quarter, and then to an eighth, and so on. So here we have an effect which depends on time in a regular way. The substance is characterized by a particular half-life. And it's this fact that allows us to use radioactivity as a form of clock. Now, I'm not going to use this particular substance as our clock. I'm going to use one called muons. Now, muons are a type of particle which are very small. They can be moved very fast, be made to move very fast, and therefore we can compare their behavior when they are traveling fast compared to when they're stationary. They also are characterized by a half-life which is very short. The curve falls off very fast, and that allows us to measure short time intervals very sensitively indeed. Right, now, how can we produce muons? Well, nature does the job for us. Coming from outer space are high-energy nuclear particles called cosmic rays. When they enter the top of the Earth's atmosphere, they undergo collisions and give rise to interactions of one sort and another, and out of the debris emerge the muon particles. But what happens to these muons? We know that when we produce muons in the laboratory and observe them when they're stationary, the time they take to halve their number is 1.5 millionths of a second, as I said before. That being the case, we would expect the muons produced by the cosmic rays to disintegrate whilst they were still high up in the atmosphere. We certainly would not expect many to survive down to ground level. But now let me show you something interesting. Many of these sparks, you can see, are being produced by muons which somehow have managed to arrive at ground level. What we've got here is a spark chamber. It's a device for detecting very tiny charged particles. It's kind of glorified Geiger count, if you like. We have various metal plates, and they're charged up to a very high voltage. And the idea is that when a tiny charged particle produced up in the atmosphere goes whizzing through the apparatus, it creates a pathway between the various plates, and it's across that pathway that the pent-up electrical charge is able to surge across and produce the spark. So, although we can't see the particles themselves, we can see the sparks that they create. But how come the muons are down here at ground level? You know, remember, they should have disintegrated high up in the atmosphere. Well, what's happening is that the internal timekeeping ability of the muons has been affected by their motion. It's slowed down, so that, in fact, the muons are now living much longer than when they're stationary, and that's how they can live long enough to get down to sea level. Okay, well, that's the qualitative explanation. Does it tie up quantitatively? Now, does it agree with the gamma factor we derived for the light beam clock? Well, in order to answer that question, we have to come to a special laboratory like this. I'm, in fact, at the European Centre for Nuclear Research, CERN, in Geneva. Now, here they don't have to wait for the cosmic rays to produce the particles. They can produce them to order. And it's here at CERN that in 1976 they did a classic experiment on the lifetime of the muon. This is a machine for storing fast-moving charged particles. and in 1976 it was used for storing muons. Now the idea is this, that you have your charged particles moving in a tube, that tube there wrapped up in aluminium foil, and above and below the tube you have the poles of the magnet, and they give rise to a vertical magnetic field. Now when you have charged particles moving horizontally through a vertical magnetic field, that gives rise to a force on the particles which is acting in the inward direction. And that then means that the particles get deflected, and they get deflected right the way around a closed loop which goes right round to the other side of the laboratory. So the tube they're passing in is actually donut-shaped, forms a complete closed loop, and so the particles come back to where they started, ready to go round a second time. The idea behind our particular experiment is that we have a tight bunch of muons going round the ring. They're going at a particular speed, which in this experiment was 0.9994 times the speed of light. And as they go round, the muons disintegrate. Now, if we're to measure the half-life of these moving muons, then we need to know how many are still surviving at any particular point in time around the ring. And we do this by detecting the particles given out by the decays of the muons occurring inside the tube. As the bunch of muons goes round, it sprays out the electron debris from the decays. First, the rate at which the electrons are emitted is high because there are lots of muons disintegrating. As the number of muons in the bunch is progressively depleted, there are fewer left to disintegrate. So, although the half-life, of course, is not changing, the actual number of electrons emitted and passing out through the walls in a given time goes down. So if we sit at a point like this on the ring, and we count how many electrons are emitted by the bunch as it goes past this point, then that number of electrons will be a measure of how many muons are still surviving in the tube at that particular point in time. Now, the counting of the electrons is done by this scintillation counter. The idea is that the electrons come out through the wall of the tube into the counter, where it gives rise to an electrical pulse, which then passes on and goes off to a computer, where these pulses are pigeonholed according to the time at which they're received, and then we can display all the results on a computer output. If we look over a longish period of time, we get a curve like this. You can see how the numbers fall off with time. We can compare this with what we would have got if the muons had been stationary. As you can see, there's a dramatic difference. For the stationary muons, the number is reduced to a half after 1.5 millionths of a second. Whereas for the fast muons, it takes 44 millionths of a second to halve their number. This difference, by a factor of just under 30, is exactly what the formula we derived had predicted. And the accuracy of the verification in this experiment was the 2 parts in 1,000. Before leaving this experiment, there is one thing that I would like to emphasize, and that's this, that this experiment obviously had nothing to do with light beams bouncing between mirrors. It was about a completely different physical process, a material particle breaking up. So this effect we've come across there's nothing special to do with light or with muons. It's to do with the nature of time itself.
The rapidly moving muon lives longer than the muon at rest, travels a much greater distance than the normal lifetime would lead one to expect. Is there a lesson here for ambitious travelers? Perhaps our normal lifetime can also be stretched considerably, and journeys over enormous, even stellar distances become biologically possible. Let's plan such a trip. We're going to take off from Earth fully equipped for a long voyage. We shall leave the solar system and head away towards the bright star Vega, 25 light years distant in the the constellation Lyra. We shall travel there at practically the speed of light. After reaching it, we shall turn around and return to Earth. The round trip will cover a distance of 50 light years. But the question we must ask is, does this mean that the round trip will last at least 50 years, a large fraction of our normal lifetime? No, it does not. Aboard the spaceship, which moves rapidly relative to the Earth and the star Vega, clocks beat more slowly, just as with the fast muon. Physical clocks and biological clocks. So the astronauts will not have aged 50 years. All right, what does happen? Well, we know that the slowing down of clocks is described by the factor gamma. If we travel at 1% less than c, 0.99 c, gamma is about 7. And the astronauts age not 50 years, but 50 divided by 7, or about 7 years. If the speed goes up to 1 part in 1,000 less than c, 0.999 c, this reduces the elapsed time by a factor of about 22, and only 2 years will have gone by. Perhaps you've been getting a bit worried. The astronauts at speed 0.99 c will travel the distance of 50 light years in only 7 years. Does this mean they travel at 7 times the speed of light? Certainly not, since no physical object can exceed the speed of light. Something new must be involved. If the spaceship, moving at practically the speed of light, requires 7 years for the journey, the astronauts must judge the distance they have traveled to be 7 light years. In other words, if the elapsed time for the voyage is reduced by the factor gamma, the distance of travel as the astronauts perceive it must also be reduced by the factor gamma. The concept of length as well as time has become relative to the observer. The Newtonian view of absolute space and time has crumbled completely. After all this planning, on with the journey.
This is SRST Dateline. Time 7:30 a.m., August 14th, 2080, and a memorable day for the local citizenry. Today at noon, a pencil-slim rocket over 500 meters high will lift off for Vega, about 25 light years distant. The mission commander is 24-year-old local boy Dwayne Anderson. Dwayne's brother Virgil is well known locally for his physical survival center. He has been giving his brother last-minute advice on keeping fit during the years of this extraordinary flight. We'll be going on to Houston for the launch later today. The Late Show will be bringing you computer-created highlights of the trip as Anderson and his team make their way beyond the solar system out into interstellar space.
3, 2, 1, 0. Plus 2. Counterclockwise roll. 4, 5, 6, 7, 8, 9. Plus 10.
After accelerating up to speed, 0.99 c, the spaceship sets out for Vega. Radio telescopes track it, and a computer displays its progress together with a display of Earth time. To the Earth observer, the rocket and all inside appear contracted in the direction of motion. All physical processes also appear to be slowed down throughout the journey. After about 25 years, it reaches Vega.
Bennett. Second stage, power supplies off. Off. Power X off. Looking good at BTL.
Looping behind the distant star, the spacecraft starts its journey home. precisely the same physical effects are observed on the return journey. And at long last, back to Earth. But how does this view compare with the astronaut's own experience of the trip on board the spacecraft? To him, the distance between the Earth and Vega, which is being covered at 0.99c, is measured at only 3.5 light years. The astronaut experiences none of the time-slowing effects observed from Earth. To him, clocks on board run normally. After 3.5 years, he reaches Vega and begins his return journey. Observations in the astronaut's visual display unit showing the approaching Earth alert Dwayne Anderson to his impending spiral back into the solar system. Home at last. The brothers meet again. This is the face-to-face confrontation between the two accounts of this epic journey. For one, a wait of 50 years has been for the other a trip of only 7 years. Are they both correct? After 50 years on Earth, the astronaut has returned, only 7 years older. But isn't there a problem here? From the viewpoint of the spaceman, isn't it the Earthbound brother who has been in rapid motion? So wouldn't he be the one to age more slowly? No, that won't do. The two brothers are not fully equivalent observers. The brother in the spaceship had to be accelerated to reach almost light speed relative to the solar system in Vega, was again accelerated to turn about at the stellar objective, and finally had to be decelerated to re-enter Earth orbit. The two brothers are certainly not on the same footing. And so the face-to-face confrontation between the young astronaut and his considerably older brother would seem to be the correct outcome of this trip of the imagination. Now, since a real trip to Vega is far beyond our present capabilities, can the essential conclusion be verified closer to home?
Well, yes, and the proof of it is right here in this experiment we were thinking about. After all, we can regard myself as being the Earthbound observer, and the muons are the astronauts. They take off and they have their journey out into space. All right, they only get as far as the other side of the laboratory before being accelerated round and back to where they started. And of course, they perform this journey many times over. Now, when there are only half of them left, as far as they're concerned, they've just undergone a normal half-life, which is 1.5 millionths of a second. But as far as I'm concerned, the amount of time that's gone past is 44 millionths of a second. Or to put it another way, suppose I had a twin brother. And the day we were born, our parents brought us here to CERN and squeezed my brother into that tube and made him go round this ring at the same speed as those muons. And suppose he's been kept going at that speed ever since. And today we come and have a look at him. How old would he be? 18 months.